Well, thank you for inviting me. I'm enjoying the workshop so far. And thanks to Roland's great overview talk earlier this afternoon, all of you are already well set into thinking of antiferromagnets not in terms of layers, but also in terms of atoms. So this is what I'm going to keep going on in my talk now. So I want to show you things that we do with the scanning tunneling microscope, where we have the ability to move individual atoms around on surfaces. So this is very similar to the things that Roland showed you in the last part of his talk, except for one difference, and that turns out to be crucial. We don't do this on a metal surface. So you're looking here at it's not apparent in images. So you're looking here at a 3D rendering of an STM image. All these atoms are iron atoms that we assemble on the surface, and the surface now is a copper crystal where we grow by self-assembly one monolayer of copper nitride on it. And the copper nitride in bulk is an insulator. In this one monolayer, it is still metallic, but it serves the purpose of sort of keeping the magnetic moments of the iron atoms intact. So if you believe density functional theory calculations, then what happens is that the iron atom gets grabbed by two nitrogen atoms, sort of pulled into the surface, and then the moment stays intact, and also we can make use of super exchange interaction through the nitrogen atom. All right, so much for the details of the sample system, and we'll keep it for the talk. The motivation of all the study is this question: can we create functionality in just a few atoms? Well, at least in a lab experiment, in a prototypical way, we can do it. The big disclaimer here, of course, is so far only with the scanning tunneling microscope and also only at very low temperatures. The very low temperatures in our case are typically 0.5 Kelvin. All right, but nevertheless, we can think of different applications that we might be using, and it turns out that we have found a bunch of things that we can do with antiferromagnets, which I guess is the reason why I'm standing here at the moment. All right, so just to get you thinking a bit more about how do we actually image magnetism in a scanning tunneling microscope, we are using what we like to call spin excitation spectroscopy. So the thing to think about is like this. We have a surface, which is our copper substrate with the copper nitride on it, and just an atom here. We can park the tip of our scanning tunneling microscope over it and then pass current through this structure, and all of the current will actually flow through this atom. In energy space, this looks like this. The tip is a metal. Then we have a vacuum barrier. The atom, which can have a few states, for example, magnetic states or spin states. The copper nitride looks like a barrier as well, and then we have the copper substrate. The normal tunneling mechanism would be elastic tunneling. That would be what you might be most used to, which is an electron from an occupied state in the tip, for example, just tunnels through everything into an unoccupied state here. In the presence of a magnetic atom, there's another possible tunneling channel, and there's inelastic tunneling. So an electron can tunnel onto a state of the atom, interact here with the electrons that are already on the atom, and for example, exchange spin momentum and energy, and excite this atom to some state, and then leave the atom again. Due to energy and spin conservation, the electron will then exit at a different energy, and it still needs to find an unoccupied state here. So what this turns out to be in an experiment is a kind of threshold spectroscopy most of the time. So here you're looking at the differential conductance, so that's the vertical axis, as a function of bias voltage we apply. So you see we apply reasonably small bias voltages. And this is the spectrum we see for iron atoms. Mostly you see these steps occurring here. So here's 0 volt, then a step, then almost constant conductance, another step, conductance again constant, or almost constant, and another step. These steps turn out to be symmetric. And this is the hallmark of this inelastic tunneling. So at every position of this step, we can excite a spin excitation in the atom. And by this, for example, we can directly extract magnetic anisotropy energies. We can extract spin Hamiltonian parameters from this just by basically fitting the excitation energies we see here to an effective spin Hamiltonian model. So the important part that I would like to highlight before we go into the antiferromagnets is here on this copper nitride surface, we deal with spins where the orbital moment is almost quenched, so it is fair to think of them just as spins. But we have to include not just uniaxial anisotropy, we have to include transverse anisotropy as well. So for the iron atom, this has a very dramatic consequence. So if we were to use a Hamiltonian that would just be like dSz square, so uniaxial anisotropy, easy axis magnet, for an iron atom, we would get these 5 states here as a function of SZ expectation value. This is just what you expect from an easy axis magnet, right? Like 2 states with maximum expectation value at low energy, and then a bunch of states in the barrier here. So, but the iron atom has this transverse anisotropy that is quadratic to at least in lowest order that we can use here. And what that does to the iron atom is it mixes all these states that are right and left of this barrier into non-magnetic states, like symmetric and antisymmetric superpositions, and they all have 0 expectation value of the spin by themselves. So the iron atom itself on a surface is non-magnetic, or at least on this surface it is non-magnetic. But luckily, by just applying a magnetic field, we can rip these states apart back into their +2 and -2 states. But it will be important to consider that there is transverse anisotropy always at play. So the fair approximation to use for these systems is a spin Hamiltonian kind of way. All right, so the rest of my talk, I want to tell you about this image in the end. This is 2 nanostructures that we've created. We've worked quite some time to understand the physics going on so that we could actually create them. And they represent a basic function, a spin sensing function. So this big structure here turns out to be a stable structure, a bistable structure. It has 2 magnetic states. They are antiferromagnets. So you might see it in this image already. It's a spin polarized image that we took with a spin polarized tip, much like Roland showed you. See, one iron atom appears bigger and one appears smaller, smaller, bigger, bigger, smaller. All of these are iron atoms, so with a non-magnetic tip, they look identical. Anyway, so, and then there's this small structure here that consists of 3 iron atoms. It turns out this is not a bistable system. This is still a quantum magnet described by spin states, and it is capable of sensing the magnetic state of this antiferromagnet, which is about 3 nanometers away. I want to show you how this works. All right, let's first focus on this guy. Actually wrote it down. Okay, so the way we build these is by going away with the STM tip and picking up an iron atom somewhere at the surface and then positioning it on the surface where we want. So if we start with this 1 iron atom, we can place another one next to it. Image looks like this. We can go fetch a 3rd iron atom and place it here. So the atomic structure or ball model structure of this looks like this. The 3 iron atoms are 2 unit cells of the copper nitride apart. So you have linking them, you have like 2 nitrogen atoms, which are blue here, and a yellow copper atom. Turns out they couple antiferromagnetically with an exchange interaction energy in the order of a millielectron volt. So we can study this in more detail using our spin excitation spectroscopy. We can do spin polarized imaging to convince us this is really antiferromagnetically coupled. You see big atom, small atom, big atom. This is purely magnetic contrast. We can do spin excitation measurements on the 3 atoms, get different spin excitation thresholds out of it, fit it to a spin Hamiltonian model. Going through this a bit quickly to show you the really new stuff in the end. The important part to consider is the result of this spin Hamiltonian. This is the energy spectrum of this iron trimer structure. So these are the low energy spin states of the structure. There's 2 states at low energy, these here. They show Zeeman splitting and a magnetic field. And then there's a gap for about 7 millielectron volt, and then come a bunch of other states. These 2 states, the red one and the blue one, are the 2 Néel states of this trimer. So up, and down, up, down. In a magnetic field, they're not the same, therefore they split. But without a magnetic field, they would be the same. So they should be degenerate. But due to this transverse anisotropy, they are not degenerate at 0 field. And we can figure out that right at 0 magnetic field, these 2 states form an avoided level crossing that has an energy splitting of about 2 microelectron volt. And this is now pretty cool, because this is all you need to create a spin sensor structure, or to create a spin sensor functionality. We have a avoided level crossing here, and we have barrier states that allow us to use spin pumping to jump, like when we go out of the avoided level crossing, to jump between these two by spin pumping methods. All right, so the way we can actually see that the level crossing is 2 microelectron volts is no longer by normal spectroscopy. We see this by pump probe methods. So what we do is we stop applying a DC voltage to the tunnel junction and go get ourselves a pulse pattern generator and send pulses down into the tunnel junction. And we can send, for example, a larger voltage pulse that is basically going above into this cloud of states here. This will create an excitation, and then we can send a smaller voltage pulse that is even smaller, or that is just a few millieV, that basically allows us to do tunneling magnetoresistance measurements. All right, so this is a quick way of saying we can take the methods used by optical pump probe spectroscopy and transfer them into the STM by using electrical pulses instead of optical pulses. And then this is the pump probe spectrum of this iron trimer. So right around 0, when the pump pulse hits, we see that the spin signal, or the spin polarized current, drops and then recovers over the course of a few microseconds back to its original value. And this decay is a single exponential decay with a decay constant of about 5 microseconds. So that means that at the specific magnetic field we used here, this iron trimer structure has a spin relaxation time of 5 microseconds. So the way we do it is similar to many other measurements. We apply a DC magnetic field so that one of the two Néel states is the ground state, and then the other one will be a metastable state. We pump it into the metastable state, and then over 5 microseconds it relaxes back. All right. The cool part now is that this spin relaxation time depends on where you are in this level diagram that I just showed you. We can check this by using a very easy magnetic perturbation that we have at hand, meaning the last spin on the tip of our STM. As Roland showed you, like even if there's only one atom here, or if there's an antiferromagnet around, there's one atom with a magnetic moment that is the last one in the tunnel junction, and it will couple to this trimer by exchange interaction, by dipolar fields, by anything magnetic, and it will influence the spin states. And depending on how far or how close this tip is, the interaction will be different. And this is what we checked here in this measurement. We just kept recording the pump probe spectra as a function of separation of the tip, or movement of the tip relative to the sample. We see as we go in closer, negative is closer. You see the signal becomes, the decay becomes faster, the signal becomes smaller, it vanishes, and then it recovers. So what's going on here? In detail, it is like this. If we have the trimer on our surface and we don't apply a magnetic field and we don't apply any perturbation, the system sits happily in this ground state in the avoided level crossing, and the excited state is this one. Both are non-magnetic. If you calculate the transition intensity between them, then you find out that the spin relaxation time of this is extremely short. But if we now apply a bias field by our external magnet, we move out of this avoided level crossing. The ground state becomes more the Néel state where the two spins are aligned with the magnetic field, and the excited state is then the opposite. And it turns out the spin lifetime evolves linearly as a function of this perturbation. And then, why is this a sensor? It's because if we add a perturbation, like the tip, this perturbation adds to the external bias field and then moves us either further out of the level crossing, which makes the lifetime go larger, or it moves us back towards it, which makes the lifetime go smaller. And it turns, like one thing we used to do with this is to measure how strong the influence of this magnetic tip is. So at this point, the STM tip had just like 3 or 4 magnetic atoms attached, and we can see now that the interaction in terms of measured now in Tesla as an exchange field, just as you approach by 2.5 angstroms, goes from almost nothing to 3 Tesla. And because of the steepness of this increase, we're fairly confident that this is really due to exchange interaction of the orbitals of the last atom on the tip and the orbitals of the trimer. And well, you can see we can create quite strong exchange fields of several Tesla magnitude. And that actually allows us to control these tiny nanostructures in a very precise way. Okay. Let's go to the other side. This is just a different image of one of the bigger structures. So it contains 12 iron atoms, 2 rows of 6 iron atoms. And as I showed you already, this structure has 2 stable magnetic states. One, you see atom is big, small, small, big. And then you can switch it, for example, by just moving the tip in using the exchange field, switch it to another state, and it's small, large, large, small. And in either of these 2 states at half a Kelvin temperature is incredibly stable. So the stability I wrote down here at half a Kelvin is larger than 17 hours. 17 hours comes mostly because then we got bored and just moved on. And anyway, so this is incredibly stable, and it turns out that even smaller structures are very stable. So here I have a chain of 8 atoms. You see antiferromagnetic order. This is now a 3D image again. So small atom, high atom, small atom. Can switch it, or it can switch on its own after some time. High, low, right? So there's 2 things that are surprising here. One is, I just showed you that 3 atoms have a spin lifetime of the order of a microsecond, or a few microseconds. Now I added a bunch more atoms, and I'm talking about stable magnets. The other one is, for this measurement, we had a field of 3 Tesla applied, and it turns out both Néel, oh, laser pointer's dying on me. Do we have another one? Yeah. All right, and it turns out, if you do statistics, it turns out that both of these Néel states are occurring exactly equal amounts of time, even in a field of 3 Tesla. So that means, essentially, to the best of our measurement accuracy, these have no net spin. So the first time I showed this, theorist jumped up at me and said, this is wrong, cannot be true. Everybody knows that finite length antiferromagnets are in the Heisenberg singlet state, which if you go to normal, like if you just write down the Hamiltonian, is completely true. But the experiment tells us differently. The experiment tells us that, at least for these 8 atoms, the Néel states are the stable states, and they're degenerate. All right, the solution to this is that it comes from looking at the size dependence of this. If you go to 6 atoms, you find, as a function of temperature, I don't want to go into detail here, just look at the constant part. You find that at some temperature, it stops changing in its temperature dependence, and then as you go to lower and lower temperature, so in this Néel plot to, Arrhenius plot that plots 1 over temperature to the right, see it's leveling off at around 10 switching events per second. If we add 2 more atoms, the temperature dependent behavior is roughly the same, but the temperature independent behavior sets on only at about 3 orders of magnitude less switching. So it's very, very drastic increase in stability. And this pointed us eventually, thanks to a discussion with Andy Millis, to theory from the 80s, in fact, open quantum systems. It is not fair to think of this antiferromagnet of just sitting somewhere on itself, so writing a Hamiltonian only for it. You have to consider the substrate. So in the most simple terms, or most general terms, maybe, you can think of the open quantum system problem here as a double well potential. So let's say this is one Néel state. I just say up. Then there's an energy barrier between and another Néel state down, right? If the system was only this, then the correct quantum mechanical solution would indeed be the singlet and the triplet state, and both of them would be non-magnetic, right? But now comes the coupling with the conduction electrons, and the conduction electrons can scatter off these spin states, and they scatter differently depending on whether the system is in this Néel state or in this Néel state. And what happens then is that, as a function of increasing this coupling, at some point you will destabilize the singlet and triplet state, and you will stabilize the Néel state. This is called this is one way to think about the transition from a quantum magnet to a classical magnet. And it turns out now, so the thing is, if you say my system without any coupling has a certain level splitting here, you can compute how much influence will the coupling to the bath be by thinking about how much the bath will renormalize this level splitting. And there's a true phase transition when this level splitting becomes 0. So for the iron chains I showed you, this means essentially this. If we compute the level splitting, this delta naught, as a function of chain length, you see that it decreases exponentially with chain length and by approximately these 3 orders of magnitude per adding 2 atoms. And when we are in the range of 2 or 3 iron atoms, we are still in this range where we have a singlet state and a triplet state, so where we still have to think of the system as a quantum mechanical system. And then as we go to longer chains, surely at the point of 8 atoms, the Néel states have been stabilized by the coupling to the environment. All right, so just to complete the picture here, if we plot the stability of this 2x6 array, we find at high temperatures it starts exactly equal to the 1x6 to just 1 6-atom chain, but then it just keeps going down in switching rate until the point where we can't measure it anymore. So so this is quite surprising that small antiferromagnets can be such stable things. And this actually, this was the last thing I did out of my postdoc time together with a group of Andreas Heinrich at IBM. Having a bistable antiferromagnet now allows you to make a prototype of an extremely dense magnetic memory, because you don't have to worry about dipolar stray fields anymore. You can just position these systems so that you use geometric frustration, that you cancel any possible dipolar fields and also most of the possible interatomic fields. So just build a bunch of these 2x6 arrays in a staggered way, and then you create a very dense magnetic memory. And the only way that it is different from a ferromagnetic memory is that for this one, you do need sub-bit resolution to read out its state, right? Like this is a magnetic contrast image of this one here, and you see in this staggered way of building it, you have 2 atoms being spin up here. The next one we wrote with spin down. And then you can go ahead and you can use spin pumping, or you can use this exchange force interaction to switch around. Okay, anyway, but this is not what I wanted to show you. I wanted to show you, in the end, the sensing. So how can we measure this now, right? Like if you, come on. So you can guess, right? Like the way this spin sensor works is that we read out changes in the spin lifetime. So what we checked for is what is the spin lifetime of this structure when the big guy is in state A, and we find one curve, and what is the lifetime when when the other one has been switched to the other state, to state B, we find another curve. And if you look at them closely, you find that they differ by about 26 nanoseconds in the spin relaxation time. And you can now either keep doing this, just keep measuring these pump probe curves and compare them, but you can do it in a more simple way by just setting your system to a constant delay and monitor the signal of your pump probe measurement. And then the system should jump between these 2 curves, so it should amplitude modulate, basically. This is the detailed mechanism. I think it's clear at the moment, but if you want to talk to me later about it, we can. I think for now, I should just show you the result. This is what we get when we do this measurement. So basically, we keep the tip positioned over this atom, and we just keep measuring the pump probe signal as time goes by. And we see this pump probe signal jumps between 2 states, and these 2 states relate exactly to the 2 Néel states of the big nanostructure. We can see that it's looking like a fairly random telegraph noise. And this is now the telegraph noise coming from this structure. So there's a few details that we're still working on. For example, you see this guy clearly switches more often than 17 hours that I showed you before. And so there seems to be some back action from measuring the trimer onto this system, which is most likely caused by hot electrons just traveling from the injection point here through the surface and causing switching events here. Anyway, but having this, we can now do things that we could not do before. This is the part that gets me excited about these things. We can now do non-local measurements, something that is very difficult in a scanning tunneling microscope. Normally, you can measure only exactly the thing that you have under your tip. And if you want to measure at different things, at different positions, you need to rely on structures being stable. With this sensor now, we can measure several nano objects at the same time. So what we did here is we built 2 big nanostructures around one of these sensors, one with 10 atoms, one with 12 atoms. And then the surrounding of the sensor has now 4 magnetic states, right? You can see in the spin contrast here. And if you again monitor the pump probe signal here, you can see 4-state switching instead of 2-state switching. And this is now the information you can take and you can analyze the statistics of this switching, and by this figure out correlations between the nanomagnets in the sensor and the nanomagnets themselves. And I think there's lots to be done with this method of measuring the magnetic information of 2 or more objects without even having your tip there. All right, so that brings me to the end of my talk. I showed you in prototypical ways we can indeed create functionality with just a few atoms. I showed you we can make bistable antiferromagnets with just about 8 atoms. We can create a fairly sensitive spin sensor with just 3 atoms, where I should point out the sensing of this thing is not limited by temperature. So it is in its detection method different from a magnetometry measurement, and allows us to be very sensitive by now. So go down into the nano electron volt level. All right, and all of this links into the idea to detect atomic scale dynamics with the STM. Then I'd like to thank everybody in my group who has been involved with this project, and particularly for the spin sensing, Xixiao Yan, who is now at the University Urbana-Champaign. The collaborators here, most of the stuff I showed you is linked to Fernando Delgado and Joaquin Fernandez-Rossier, who gave us theory support to understand this quantum to classical transition. Yeah, and thank you for your attention.